So one little thing, couple little things before we get really going with the first session. I moved the mic down into here because I was hearing from Zoom folks that they were getting background noise, and it sounds like that helps. So let's leave it down there. And then for folks in Zoom, if you need to reach us here at the Rich Earth Institute, please directly message Julia, because the main screen can't really keep track of the chat. It's usually not visible. So please message everyone or Julia directly. Thank you. So let's go ahead and get started. Mike is going to be moderating our first session. I'll let you take it away, Mike.
Good morning, everyone. So this first session on Wednesday is the implementation projects, nutrient cycling for clean waters and fertile farms. One note is that we are not having a presentation by Hannah Vandenbergh. She's not available this morning, so that one is not happening. But the good news is we will have a few extra minutes to do Q&A in this session.
You guys hear in the back? Okay, we got to be real loud.
I'll turn up my volume. Earle Barnhart and Hilda Maingay is the first presentation from the Green Center on Cape Cod, Massachusetts. They conduct research and provide education about urine diversion. They have used waterless nutrient recovering compostable toilets in their home for 24 years and added urine diverting fixtures to their existing eco toilets 10 years ago. They have recycled all their human waste nutrients and kitchen scraps back to their extensive home food production gardens since the year 2000. And they will be presenting on the Green Center Cubie-Based urine diversion pilot study. Wow, that's quite a feat. So Earle and Hilda, they're present, or are they on Zoom?
Yes.
Okay, go ahead, Earle and Hilda.
Okay. There we go. Can you hear me? Your sound is not on.
Yes, it works.
Can you hear me?
Yes,
okay.
Go ahead.
Okay. Thank you very much for having us. Thanks the Rich Earth Institute for having us. Hilda and I are both here. We are involved with the Green Center, a nonprofit on Cape Cod, Massachusetts, USA. We live on a peninsula made out of sand with thousands of people living on it. They all have septic tanks. The urine from their toilets are flushed into the septic tanks and go into the groundwater. And so most of the groundwater on the Cape Cod has too much nitrogen in it. It's causing pollution on the coastal water. It's causing pollution on the freshwater ponds on the Cape. And the reason is that the urine that goes into the septic tanks from the flush toilets contain 80% of the nitrogen from the home and 55% of the phosphorus, but it's only 1% of the volume of the water leaving the house. So the most efficient way to control the urine that's polluting the Cape is to stop the urine from going down into the septic tank and into the groundwater and polluting the natural waters. Our town is called Falmouth. It has 30,000 people. It's in this picture. And if you look on the shoreline of the Cape near Falmouth, the nitrogen is seeping out of the ground into the ocean and causing pollution and algae growth along the edges, as well as in all of the water bodies on the land. Cape Cod has 890 freshwater ponds left over from when there were glaciers here. 1/3 of them are so polluted with nitrogen and phosphorus from the housing that they grow cyanobacteria, toxic, dangerous bacteria on the surface of the water, usually in the summer, and it's poisonous. You can't touch it, you can't swim in it, you can't drink it. If your dog swims in there, your dog will die. It's a very serious problem, and it's one of the major incentives for Cape Cod to try to figure out some way to control the nitrogen. Wait a minute. So normally in a house on the left at the top, all of the nutrients from the house goes into a septic tank and down into the ground. What we've proposed is you have a second tank near the house where the urine is collected and kept out of the ground. All of the rest of the nutrients from flush toilets and gray water goes into the normal existing septic tank and drops down into the groundwater. That's only about 10% 20% of the nitrogen. So we're taking 80% of the nitrogen out of the groundwater, collected as urine, and transporting it away to other uses or to disposal. When we proposed that the town use this technology, they said, well, how much urine can you collect? And we had someone research it, and there was no good data anywhere in the world for how much people could practically divert and collect. So we decided we would do a study here on the Cape to find out. This study had never been done before. What we did was we gave out cubies from the Rich Earth Institute to 41 homes, and they collected urine voluntarily in each home. Each home averaged about 1.5 people who were doing this. They put the urine into cubies, then they put the cubies collected and put them into 55-gallon plastic drums. And then for 2 months, we did that. We use cubies because they are perfect for this experiment. They're cheap, they're easy to use. Men and women can both use them. They're portable. You can put them in your bathroom. You can put them in your back porch. You can put them in your garage. You can put them anywhere. They have a ball in the Cubie's funnel so that the urine goes down, but the air does not come up. Odors don't come up. This is a standard Cubie that we used. Men and women can both use these Cubies. Men stand up in front, women squat down behind. And in 1 year, if a person collected all of their urine, you'd get 120 gallons per person. We collected for 2 months, and then we extrapolate up to a year to see what would happen if you did it for a year. So the logistics of this was the person would collect in the Cubie. They would dump it into the 55-gallon drum with a non-touch spigot developed also by Rich Earth. So that was necessary for our Board of Health so that people did not touch the urine at any point in the process. We collected the urine for two months in each home. At the end of the 2 months, we would measure the depth of the urine in the tank. And depending on how deep it was, we calculate how many gallons were in there. And then a sample was taken from the drum to test for the amount of nitrogen and phosphorus in it. And it was stirred first because the struvite crystals sometimes go to the bottom and should be included in the sample. So it was stirred and then tested. The sample was taken to a county lab, so it had a high quality proof of what was going on in it. It was the Barnstable County Water Lab. Each home then was given results of how much nitrogen was in their urine. And then with the amount of nitrogen in the urine and the amount of urine, you can find out how many pounds of nitrogen was collected in these drums. At the end of the 2 months, we had Wasted come by, pump out the 55-gallon drums, take it away, and take it to an approved disposal place. For each of the homes, different amounts of urine was collected. Some collected a lot, some a little, depending on how many people did it, how often they did it, whether they went away from home for a while. These were like average conditions for average people. The least collection was 9 gallons, the most was 71 over 2 months, and the average was 29. The science of this project was managed by the MASSTC Alternative Septic System Test Center on the Cape. Bryan Horsley, who's at this summit now, was the person who did the measurement and the sampling and the collection and write the report. The final report was published by MASSTC, and it described the process, it described the findings, and it described the implications of the advantage of this. And the basic quantitative information was it showed that 2-month study, typical household, 1.5 people, if you extrapolate that up to a year, would remove 9.7 pounds of nitrogen and 0.64 pounds of phosphorus from a home using Cubies voluntarily in this manner. This is about the same amount of nitrogen removal as a sewer when you do the numbers, and it's at a tiny, tiny fraction of the cost of a sewer. Now, what's important about this project, among other things, is the use of the Cubie. This project was possible because of the Cubie. No one else has done this kind of experiment in the world because it costs too much to install fixed urine fixtures in homes, and that's a barrier. But a Cubie is cheap, mobile, free, or relatively cheap, and allowed this to be done. And the important part of this is that Matthew Lippincott, who probably is at this conference, made the statement after the report that the Cubie is not a permanent solution, but it's an affordable analog of a permanent solution. So we could, if you did install permanent urine diverting fixtures in these homes, urine diverting compost toilets, urine diverting flush toilets, any kind of urine diverting fixture, you could get these kinds of results, but it would cost a lot more and it would be more difficult and slower. But with the Cubies, it's as if you had done that. You get the same information as if you had done that. That's the general overview of our project. Thank you very much. Hello?
Thank you. Thank you, Earle. Yeah, I'm just. Okay, thanks for that, Earle.
Yep.
The next, how do I change the view? Is this
Excellent.
Forgive my technical difficulties here. Okay. So the next presenter is also from Massachusetts, from Cape Cod. His name is Bryan Horsley. He's from the Barnstable County Department of Health and the Environment, also known as MASSTC. He helps out with a wide range of projects, from installing and testing innovative nutrient-removing septic systems to facilitating acceptance of ecological sanitation practices for pollution source control. Bryan will be presenting on what's up with urine diversion on Cape Cod. Bryan, are you here? Here he is.
I'm here. Can you guys hear me okay?
Yeah, we hear you great. Go ahead.
Okay. Let's see, I'm gonna click this. All right. Okay, so here we go. So I think Earle's presentation was sort of a great intro into mine. As he mentioned, I helped him out with that Cubie project, and now we're looking at how we can implement urine diversion on sort of a larger scale on the Cape, and how we can utilize it in such a way that municipalities can actually get credit for the amount of nutrients they're removing using urine diversion. So first off, I wanted to start just by introducing the test center where I work. So we're a division of the Barnstable County Department of Health and the Environment. So we represent all 15 of the towns on Cape Cod. We are basically a 2.5 acre testing facility where we provide a testing grounds for innovative alternative or advanced nitrogen removing septic systems. We're also very interested in ecological sanitation systems like urine diversion and composting toilets as alternative means of removing nutrients from wastewater to improve water quality. So, really the reason we're talking about Cape Cod so much, as Earle mentioned as well, is that, the majority of our waters on the Cape are impaired. And this is a big problem because, Cape Cod is really dependent on its blue economy. Previously, historically, the Cape is, it's named after a codfish. The place was, all about fishing. And that's, changed in recent years to where it's more of a tourism economy. But either way, water quality is, our most important natural resource. And these two maps basically show the marine embayments, or the extent of water quality degradation in the marine environments and in the freshwater pond environments. In the marine environment, the recent water quality monitoring data has found that about 90% of our coastal water bodies are unacceptable water quality, need restoration right away. And that's mostly due to nitrogen pollution. In terms of freshwater ponds, we have somewhere between 800 and 900 freshwater ponds on the Cape, and about 37% or so are unacceptable of the freshwater ponds. Typically, phosphorus is considered to be the pollutant of concern in those water bodies. So the next question is, what's causing this water quality degradation, both in our coastal waters and our freshwater ponds? And it's, widely agreed throughout the region that the primary source, about 80% of the source of nitrogen, is from these conventional on-site septic systems. Basically, all these systems do is collect wastewater from homes and then put it underground to keep people safe from pathogens. But the problem with that is that they don't do anything to remove the nutrients. So they're basically transferring nutrients to the groundwater, which then flows into surface waters, causing the degradation that we're having. So the Massachusetts Department of Environmental Protection, so our state environmental regulatory agency, is requiring that towns do something about this. And so they're basically the regulatory teeth are into the towns and asking them to come up with what they call watershed management plans to improve water quality in all of those impaired waters. And so those watershed management plans entail kind of a variety of strategies, which I'm going to get a little bit more into here. So this overview map of the Cape shows basically the areas that are sewered in dark black, and then the green areas are open space, and the brown areas are areas that are dependent on on-site management of wastewater. So currently about 85% of the Cape is reliant on on-site wastewater management. Like I mentioned, that individual towns are working on planning to improve water quality through their watershed planning. Many of them are relying on expanding their sewer systems. So they're actively working on that. Some of the problems with that, though, are one, that it's extremely expensive. Two, that it's really going to take decades to implement those systems. The town of Barnstable, where I live, is basically right in the middle of the map there. It's sort of the biggest sewered area, has a 30-year plan to expand their sewer area to improve water quality. So most people feel that these systems are too expensive and are going to take too long. And then the other problem with relying on sewering and watershed planning is that at best, sort of the maximum sewering plans will cover about 40% of the homes on the Cape, leaving the majority, 60%, to still be addressed with on-site either advanced septic systems or other approaches. And that's my segue into urine diversion, because we are looking at urine diversion and composting toilet systems as an alternative that could do similar work, or the same work basically in removing nutrients, but with all the other benefits that we've been talking about in this conference, allowing for urine recycling, likely doing it less expensively, and likely doing it with less energy intensive use. So if you look at this map here, on the far southwest corner is the town of Falmouth, like on the bottom left of the map there. And this is the same area that Earle focused on his talk as well. So this map shows a zoomed in image of the town of Falmouth, and this is basically the town's active watershed management planning map. And so you'll notice there's all these polygon areas, sort of these long, sort of curved shape, black lined areas. These are the individual watersheds in the town of Falmouth. So basically what that means is that all of the homes or the businesses that are within those individual areas, any wastewater that enters the ground at those locations is going to travel to a receiving water that is probably impaired. And so within those individual watershed areas, the town is using basically working on two different approaches here. So you can see that the light green is the areas that have already been sewered. The dark green areas are the areas that they're planning to still sewer. And then the blue areas are the areas where they're recommending installing advanced treatment septic systems. So, we as the county, and working with a group of colleagues, are looking at this alternative approach of how we might be able to include urine diversion in this watershed planning strategy. And that the town is also very much involved in working with us to explore this effort. So where we're at right now in sort of assessing urine diversion for a good fit into the watershed planning process is working on the regulatory approvals. Those are kind of the biggest hurdles we're facing right now. So the first one is working with the Department of Environmental Protection. That's, again, environmental regulatory agency. With them, we're looking to get approval, and that approval will basically be what outlines how much nutrient removal credit the towns can get for installing urine diversion systems. So we're making progress there. The other regulatory agency that we're working with that's very important is the Massachusetts Plumbing Board. Currently, most urine diversion fixtures are not approved in the state of Massachusetts, and nor are the collection system plumbing and the storage tank. And so we are working on updating some plans and plan to participate in a hearing in front of the Massachusetts Plumbing Board to try to get approval for both the toilet fixtures and the associated plumbing systems. Once we gain the approval to collect the urine and get the credit for removing it, we then need to figure out what we're going to do with all of it. Again, in the state of Massachusetts, we don't have approval to land apply urine as fertilizer. So we're working with the Division of Agricultural Resources to try to gain that approval. We're also looking at all other strategies for treatment and processing of urine to make it a viable fertilizer. And then, of course, we need funding because, as the next slide will describe, we're needing to install 50 urine diversion systems and sample and monitor them for a period of 3 years in order to meet the requirements from our Department of Environmental Protection. So that's the plan. Right now we have a list of around 150 people, which the Green Center have helped compile among other colleagues. And we're looking to install 50 urine diverting systems mostly in residential homes, and then sample and monitor them for 3 years. And the goal of that is to gain a better understanding of what total nitrogen or phosphorus load we can remove from the watershed. And there are two different ways of looking at it. One is sort of cumulatively, if we collect all the urine within an impaired watershed, measure the nutrient concentration, measure the volume, then we can say exactly how many pounds or kilograms of nitrogen we removed from that watershed, and hopefully the town will be able to get credit toward meeting their water quality improvement goals. The
Bryan,
alternative
we've got 1 more minute.
Sorry, what was that?
We got 1 more minute on your presentation.
Okay, this is my last slide. And so the alternative way to look at it is by measuring the remaining nitrogen content in the septic tank. What that will do is allow us, basically to see how much nutrients are left over after doing urine diversion, and that will allow sort of an apples to apples comparison with the advanced septic systems. And the overarching goal of all of this is to explore, whether urine diversion can remove enough nutrients from these impaired watersheds to work towards those water quality improvement goals, and potentially offset the need or reduce the need for expanded sewers or mandated installation of IA septic systems or advanced treatment septic systems. So lastly, I just wanted to thank all the participants. Like I mentioned, we're working with the town of Falmouth. We're working with the Rich Earth Institute, University of Michigan, Nutrient Networks, Point of Shift, and then the last two are from the county where I work. So thanks very much for listening. And I'll get out of here.
Thanks, Bryan. Thanks for that presentation and for so clearly outlining the problems on Cape Cod. And I'm sure that those problems are not just specific to Cape Cod. They exist in many, many other places around the world. Okay, so next up, we have a pre-recorded presentation from Louise Raguet. She is a designer for the OCAPI Research program in France, specifically Paris. She develops projects for ecological sanitation and especially urine collection in urban context. As a freelance designer, she developed the female urine named Marcel and recently released the unisex version. Very exciting. Louise will be presenting on the nutrient cycle in a community-supported agriculture in the Paris region.
Hello everyone, my name is Louise Raguet. I am designer based in Paris. I work for the OCAPI Research program, and I recently developed a small-scale project for urine source separation called Enville. The project takes place in the context of community-supported agriculture. A community-supported agriculture, or CSA, is a system connecting farmers and consumers. Consumers subscribe to the harvest of the farm, and the farm delivers vegetable every week. This is a mutual commitment for the whole year. For the Enville project, we had the willing of reproducing a community of pea cyclers similar to the Rich Earth Urine Nutrient Reclamation Program. We also wanted to take advantage of the existing logistics between farms and consumers. Thus, the idea of the project was to install a urine depot very close from the place where vegetables are delivered by the farm and dispatched between consumers, so that pea cyclers who collect urine at home can bring their urine container every week when they come and get their food. On the contrary, the farm can collect urine during the delivery and bring the nutrients back on the farm. This way, no additional tanker truck is needed. For designing this project, we identified the participants at the very beginning in order to get their opinion on the use and design of every step. We developed the urine channel little by little so that we could adjust and adapt as we went along. I will present now how it works today on November 2024. Of course, we were very inspired from what the Rich Earth Institute developed and experimented, so thank you for inspiring us. Now, let's talk about urine collection at home. In accordance with participants, we decided to use this kind of 5-liter can. These are very easy to find as reused container, since this is the format of most of the cleaning products for public spaces. We also designed a specific funnel for this container with a screw on and a cap to prevent odor. For now, it's just 3D printed prototypes that we gave to the pea cyclers. For participants who can't or don't want to urinate directly in the funnel, they would use an intermediate object. We had several types to offer, depending on the feeling of the person. Then, when the container is full, it's time to go and empty it at the urine depot. So we are here, close to the place where the consumers of the CSA group come and get their vegetables every week. It is a public garden, and the dispatch of the vegetables takes place in a building that belongs to the city council. Pea cyclers come walking or biking because they all live pretty close from here. That's also why we have chosen 5-liter containers so that they don't have to carry too much. So here is the door where there is the room with the vegetable dispatch, and here is the door of the urine depot. The advantage of this place for the depot that is almost outside, and also it is in a part pretty hidden from the rest of the garden. The room is really small. We could only install 300-liter tanks. Of course, we got very inspired from the Rich Earth Institute urine depot by adding a pumping station. The principle of the pumping station is that we prevent spills and odors, and also the purpose is that pea cyclers can empty their container very quickly and very easily. So I'm going to make a demo of the pumping station. So pea cyclers put the 5-liter container at the place. Then people open the container, take the pumping stick and plunge it in the 5-liter container. After that, you just activate the pump and it will pump out urine in the tank. And it's done. There is a vent that brings all the air from the tank outside of the building so that you never smell the air of the tank. They also have soap available and hand sanitizer. When the 300-liter tank is full, Then the pea cyclers have to contact the farm, but also to put this sign on the top of the pumping station so that people know that the tank is full and you can't put your urine anymore in it. Urine collection by the farm. When the farm comes for delivery, they can get urine in their truck. They just have to turn these valves so that it will reverse the pumping system. Thus, it means that when you activate the pump, it takes urine from the tank and bring it outside in another pipe. We installed specific tanks in their delivery trucks so that they can transport urine safely. We decided to install them permanently because other configuration with foldable tanks or portable tanks didn't seem convenient for the farmers. Since the truck is totally full of vegetable crates for the outward journey, we decided to install the tanks above the wheels in the back of the trunk, where no crates can fit. As I said, farmers use the same pump as pea cyclers. They just move the valves to modify the pumping configuration. They can fill their truck in about 15 minutes, which is not that fast, but okay for the time they have. Also, the capacity of the truck is right above the capacity of the urine depot so that it would never overflow in the truck. Everything was designed in order to prevent spills and odors and to make sure that no one is exposed to urine. Farmers just connect pipes and activate the pump. Small valves prevent piping from dripping. Odors are managed through a vent that is connected on the tank and goes far from the handler. Then, when their tank truck is full, the farmers are ready to bring back nutrients on the farm. Urine transfer at the farm. The farm is located 90 kilometers away from Paris in the south direction. When they come back from delivery in Paris, they empty the urine tank from the truck to a bigger tank staying at the farm. They have also a second pump available at the farm for this second transfer. Since people from the farm don't have a lot of time for this task, we paid attention on the fact that they don't have to manipulate urine or dripping pipes. Thus, they have a box available for urine transfer with dedicated pipes and the pump. They connect the pipes to the tanks and the pump. Everything works with easy connection device so that you can plug and unplug very easily the system. For example, we designed this simple cap for the storage tank so that pipes are not plunged directly in it, which would have been very unpleasant to unroll them back afterwards. Pipes are directly connected to the cap. All these precautions with pumps and piping connections were applied because we think that otherwise the project would have been too constraining for people from the farm. Urine fertilization. For treatment, urine is stored on the farm at least for 6 months, as recommended by the World Health Organization. For now, we only made small tests on the farm in 2023. Indeed, we preferred to focus first on the design of device and protocols for offering convenient logistics between inhabitants and the farm. This farm has vegetable fields but also cereals and flowers. We applied urine on few crops either with a watering can or dripping system. As I said, because we didn't have enough time, the farm only proceeded on small fertilization tests, but no real agronomic testing or big-scale fertilization. For example, urine was applied on a strip in the middle of a wheat field. Even very small, this kind of test had major impact on the farm's willingness to follow up the project and proceed with urine fertilization for the coming years. These first fertilizations were also an opportunity to investigate the existing tools for urine application, following the WHO instructions for safe conditions. We used, for example, a fertilizer Venturi injector or a motor-driven pump. After these first explorations of urine application in 2023, we decided in January 2024 to take time to develop a specific tool for urine injection in the soil. This tool is also presented by my colleague Loïc at the agricultural session. Since urine has been collected for about 1 year, we hope to do more urine fertilization with this farm in 2025. For now, we have about 25 P-cyclers, and unfortunately we won't be able to get more than 50 people in this configuration because the tank of the urine depot and in the truck are pretty small. That said, our goal was to demonstrate that it is possible to organize a urine collection project based on a CSA in a dense urban area without changing your toilet. This is a very symbolic project, and our idea was to make a functional demonstration so that other groups of people can copy the system and adapt to their own context. On that purpose, we published a report explaining everything we've done. And we also published all the plans of the device we developed. The documents are available online on the website of OCAPI program. The system is functioning since January 2024, but we made a great opening party on September 2024. That was a good opportunity to raise awareness about urine source separation, and we've got a lot of journalists coming. From this moment, we got at least 5 other CSA groups around Paris and further in France who are willing to develop similar projects. Thank you for watching this video, and please contact us if you are willing to know more about the project.
Well, that was wonderful. I don't know if anyone else was able to use your hide and find eyes and spot the golden funnel on the shelf behind Louise. She's a former winner of the Golden Funnel Award. So it's really inspiring to see that project happening in France. So next up, one note I want to mention for anyone who has a question in posting it to the comments, please place the name of the person who you're addressing before your comments so we're able to sort them out and get them to the proper destination.
Yeah.
Yes, Julia knows how to do that.
Yeah. I'll do that.
While she's doing that, I'll introduce the next speaker. Next up, we have Marius Klinger. He is an environmental engineer and co-founder of Aneco, a Geneva-based association in Switzerland that promotes the valorization of wastewater resources and develops circular sanitation projects in rural and urban areas. Marius will be presenting on decentralized implementation of the Pitribon system in housing cooperatives.
We'll put up the contact slide at the next break. Yeah.
Marius, are you here? Looks like
Yes,
Marius.
I'm here.
Okay, great.
Can you
We hear you.
can you see
Yep.
my screen?
Yep, go ahead. You're all set.
You see the presentation? Perfect.
Yes.
Okay, so hello everyone. So as presented, I'm Marius Klinger from Aneco, Geneva-based organization. And today I'm going to quickly present Aneco, the Pitribon process, the existing pilot installations and the upcoming systems, as well as the business plan choices for the future. So at Aneco, we promote the valorization of wastewater resources and develop circular sanitation projects in rural and urban areas. And in order to understand a little bit our choices also, we try to follow as closely as possible our values, which are horizontal governance, knowledge sharing, which also means that we don't patent our technologies, but that we protect them with Creative Commons licenses. And we also look for nature-based and low-tech solutions. Our 3 main activities axes are the expertise and implementation of decentralized sanitation solutions, research and development, and awareness raising. The main technology we are developing and promoting are vermifiltration to treat the wastewater, the Cacarosel, which is a dried vermicomposting toilet, and the Pitribon filter, which is a stabilization technology for urine, which will interest us today. The Pitribon process is basically a gravity-driven biochar filter in which nitrifying by microfauna stabilizes the urine that percolates through it. One treatment unit, like you see in the middle of the picture here, sketched, has a diameter of 60 centimeters and a height of 1 meter 70 centimeters, and is able to treat the urine for 15 people equivalent, to give you an idea. The urine arrives on the top of the filter in the feeding tank and slowly percolates through the different layers of biochar, fine biochar, then coarse biochar chips, in which the urine is stabilized by nitrification, basically. Here, the most important parameters to control and to monitor for the process to work are temperatures, of course, oxygen availabilities and retention time in the filter. For us, the pH is very good of the product, is a very good indicator of how well the process is working. Smell is another one also. In good working conditions, there is no smell, and as soon as you have smells, you know that something bad is happening. We think this system is suited for small to medium installations from 1 to about 500 people equivalent. And to increase the capacity of the treatment, you need to add more treatment unit like this one in parallel, basically. The composition of the product itself is very similar to urine composition, with specificity that the nitrogen is split in two between ammonia and nitrate because of the nitrification, and the pH is around 6. In Switzerland, large-scale use is not possible of human urine products is not possible without a certification by federal authorities, like Vunanexus has done with the Urine quite some years ago already. So in order to get this certification, we need to provide evidences about the innocuity of the product and provide evidence that the process reduces pathogens and micropollutants. And the research that is needed to obtain this certification is starting, has slowly starting this year, and will really start fully next year. And we are aiming for a certification by 2027. Now I'm going to present quickly. I'm going to show the different pilot sites where the filter and the filters have been implemented. The two first pilots were installed in the housing cooperative Equilibre in Geneva. The first one here in Crécy in 2018 with urine diverting dry toilets. For now, the filter treats the urine from 3 households from on the 13 households that live there, and is constructed in the basement of the housing cooperative. And there is plan to connect all the households to the treatment. The second one is in Meyrin, also in Geneva, constructed also in 2018. And here the system is constructed outside in a little shed below the households the apartments that are connected to the system. For now, there are 5 households connected, 10 more can be connected to the system. And here, the toilets that are connected to the system are the Vossmann urine separated flush toilets. Recently, we had a new unit installed near the Alps for a new family house, which needed to treat all of their wastewater. We separated the urine with the Lauf and Save toilets and installed also a Pitribon system there. And very recently, also near Paris, an installation was constructed, and where the system must treat the urine from many urinals from one office building. The annual volume here are estimated to 18 cubics, and I'm not sure whether they already have yet started operation or not. This have to be follow up, basically. Now, except from this last system, we're mainly working in Switzerland, and actually mostly in Geneva region. And with the next planned upcoming system, we are also changing scale with the next system in Archipel here, which will treat 100 people equivalent urine production, and that should start operation around the end of next year. All these future projects are basically housing cooperatives that decided to implement in the Geneva region urine separation, and for most of them also wastewater, decentralized wastewater management and treatment. And basically by 2029, we should increase the total production up to around 850 cubic per year, if the estimates are correct and if everything goes smoothly, which is not often the case. So we will see. And as you can see, these are a lot of different decentralized site production. So in order to manage all these decentralized sites production that are going to pop up in the coming years, the current plan is to build a cooperative of producers with in it all the producers of the Pitribon. That means mostly the housing cooperatives now with Aneco also. And the goal of this structure will be to set a common price that will allow kind of a return on investment for the cooperatives, make the connections between the producers and the users of the fertilizer, that be the agriculture, the cities, horticulture, or community or private gardens, etc. Potentially provide buffer storage capacity for surplus production that may happen during cold months, for example. In all our designs for the cooperatives, there is a storage for the product on site for 2 to 3 months, but that might be necessary to provide some buffer storage. And some other roles that need yet to be defined also. This is really to be constructed, but that's basically the ideas that we discussed with the different cooperatives. And the quality control and certification of the product will be done by Aneco, as it is mandatory in the framework of the certification process in Switzerland. I think that's it for me. So thank you very much for your attention, and I'll be very happy to answer any questions.
That's wonderful. Thank you. Thank you, Marius. It's great to see what's going on with the Aneco company and your decentralized implementations. So next up, we have a person who's here in person, Benson Colella. Benson is an engineer at Wasted in Burlington, Vermont, and holds an MS in chemical engineering from the Worcester Polytechnic Institute. He was introduced to urine diversion as an intern of the Rich Earth Institute in 2019, where he worked on the development of a urine freeze concentrator, among other assignments. Benson will be presenting on urine to fertilizer in Burlington, Vermont, process and characterization. So come on up, Benson.
Oh, this is the one that, sorry. It's gonna take me a second if you're probably gonna be faster. Yep. No, you did it. You did it.
So yes.
I think that's it. We're good.
Great. See you.
Thank you.
Thank you.
Hi there. I'll be talking about 3 things today. Those are where we get our urine, how we treat that urine, and the quality of that resulting fertilizer. Gonna move kind of fast. So the vision here at Wasted is to catalyze circular sanitation and change the way people think about waste. So we are doing that as a portable restroom operator in Burlington, Vermont, and Boston, Massachusetts. So in Burlington, Vermont, where the regulatory landscape allows it, we collect urine from portable toilets in a restroom trailer. We treat it for beneficial reuse, and we land apply it while conducting some research. We are also sellers of an off-grid toilet. So that's a urine diverting composting toilet with a conveyor belt flush. And we have one in the back here for you guys to check out. And we consider that toilet on grid when it's plumbed to a collection tank that waste comes and pumps out to P-cycle. So how do we get our liquid gold? This starts with our specialized pump truck. So while most porta potty trucks have 2 tanks, one for mixed waste and one for freshwater, ours has 3, with that third tank being for urine. So that tank makes up the back portion of the truck, and you can see a yellow hose, which is used for pumping urine only. Now that truck is used to pump from 30 portable toilets with standing urinals. So those urinals divert to a bladder hidden within the mixed waste tank, so it doesn't look like a urine diverting toilet at all. Now this was a relatively costly retrofit, but it served as a good proof of concept, and we're looking to make some improvements in the next iteration. We pump also from our VIP trailer. So this is a restroom trailer with 2 of those off-grid style toilets. So that toilet there, that black thing in the bottom is a conveyor belt. It brings poop out the back to a chamber, and pee runs down the front into some plumbing and a collection tank. So this is relatively new, but it's increased our urine collection about 20% in the weeks it's been in use. And the good thing about this setup is it collects from both the standing and the sitting peers. And lastly, we collect from on-grid installations. Those are permanent or semi-permanent outhouses with that urine diverted through that off-grid toilet into a collection tank. Okay, how do we treat the urine? We have a very simple treatment train centered around technology built by Brightwater Tools. So to the left there, we have our Brightwater pasteurizer, and in the back is our Brightwater struvite reactor. Treatment begins with urine being pumped into the building under the truck's pressure. We then pasteurize it for pathogen reduction following the EPA's 503C biosolid standards. After that point, the fertilizer is considered legal for use in Vermont. But because we work in the Champlain Valley, which is phosphorus constrained, we take this a step further and strip the urine of its phosphorus as mineral struvite. So with the addition of magnesium chloride, or pet-friendly road salt, the struvite spontaneously drops out of solution, and we filter and wash it. So this creates 3 real end products. Those are pasteurized whole urine with the phosphorus in it, pasteurized stripped urine, which we more often land apply, and struvite, which is our solid fertilizer. So we've taken a few measurements from our tanks to estimate reactor performance, and we see near complete reduction of phosphate, about 85% reduction in total phosphorus, and measuring our wash water, only about 0.1% of the phosphorus in urine ends up going down the drain. So this treatment costs us operationally about 33 cents per gallon, and we can compare that to 10 cents a gallon, which is the rate the wastewater treatment plant charges us to dispose of any kind of waste, urine or mixed waste. So we're not too far off, and it's good to keep in mind that the 10 cents they charge us is not at all reflective of their true cost, because urine is such a high strength stream and because it's so costly to treat for nitrogen. And most of our cost here is labor, and much of that labor is spent just watching urine as it's pumped into the building. So with any real sort of scale, automation or engineering controls can bring that cost down significantly. Okay, what is the quality of the resulting fertilizer? I'm not going to spend too much time here, but I think it's in everyone's interest to be as transparent as possible with safety data to help advance regulatory pathways together. So things are going to pop up quick, but if you'd like more information, feel free to email me after the presentation. So we've tested our stripped urine and our struvite for 24 PFAS analytes, heavy metals, and pathogens as part of our regulatory testing in Vermont. That stripped urine measured no detect for all 24 PFAS compounds tested, and measured no detect for fecal coliform, which is our pathogen indicator. Stripped urine measured at least 2 orders of magnitude below Vermont limits for heavy metals. In terms of struvite, we measured no detect for 23 of 24 PFAS, detecting only PFBA at 1 part per billion. And again, our pathogen indicators here, salmonella and fecal coliform, measured below detection. Heavy metals in struvite measured at least 1 order of magnitude below the EPA's limit for biosolids, which happens to be most state limits for specialty fertilizers. Okay, what's next for wasted? We are very excited to be launching We Bloom, which is the name we've given to our struvite fertilizer. We have some in the back for you all to take home. So this was approved just last week for sale as a specialty fertilizer in Massachusetts, right? It might be the first urine fertilizer in the state, not too sure. So I'm very excited about We Bloom because it seems the sale of this fertilizer could cover operational costs of treatment and collection and will help us to drive greater urine collection. So to collect more urine, we're looking to expand our urinal arsenal, and that's with T Blue Star. So T Blue Star is one of our toilet manufacturers, and we're working with them to develop a combination urinal and tank. And this is something we could literally snap into our existing toilets with no other changes. So it's a very attractive option. And to do so in Vermont would bring on another 100 or so toilets to collect about 10,000 gallons per year. We're talking with Massachusetts regulators, the DEP and DAR, to build a processing pathway there. And if and when we get a pathway there, we can drop these into our Boston market to collect about 28,000 gallons per year. So Wasted is going to continue to lean into the sort of specialty fertilizer, home and garden space, beginning first with We Bloom and hopefully branching next into a nitrogen product, something like an ammonium liquid or a nitrified liquid. And we are very much looking for technology partners in that development. We're going to continue to operate as a portable restroom business. And in doing so, we're very well situated to move waste around above ground. So we're open to collaboration opportunities there where we can help provide that as a service, such as the Cape pilot projects. Thank you for your time, and please email me with any questions.
That was awesome. Thank you, Benson. It's really great to see what y'all are working on in Burlington, and super cool to see that you've got the certified fertilizer in Massachusetts. Okay, so next up we have Nadège Duchambrier. Nadège is the co-founder and chief technical officer of Vuna Nexus in Switzerland. Nadège is an environmental engineer from ETH Zurich. Specialized in wastewater and decentralized sanitation and urine treatment. Nadège is presenting on urine nitrification in Switzerland and Europe and updates from Vuna Nexus.
Thank you. Can you all hear me and see my presentation?
Yes, we see your presentation. Go right ahead.
Perfect. Hi, everyone. Glad to be here again this year. Since I thought that there was going to be some people who saw my previous presentations the other years and some who don't know anything about us, I'm going to try and do a mix that might be interesting for those who saw already what we did. So basically, the way we collect the urine is mainly in office buildings, usually with flush toilets from the brand Laufen. They call it the Laufen Save. And for those who don't know it at all, I'm very quickly going to explain it. So the idea is to use the teapot effect. And this is a separation without any mechanical system. So the idea is that the urine, which flows quite slowly, goes into a separate pipe. When the water flushes, it goes above this trap, and then a little part of the flush at the end can still enter this trap in order not to have urine accumulated in the trap. So this is what is installed in some office buildings here in Switzerland and in France. And we have a treatment system downstairs and basically in the cellar where we treat directly the urine and make everything on site, basically, where the final fertilizer is also produced. So I'm just going to go very quickly through the steps. First, we have a collection storage system where urine is just collected from the different toilets of the building. The main part of our system is a biological reactor. It allows for nitrification, partial nitrification, which is basically that we give urine and air to bacteria, and this bacteria eats the urine, transforms the ammonium in the urine into nitrate, So in the end, we have a liquid which doesn't smell like urine anymore, and which is ammonium nitrate. And it still contains all other nutrients that you can find in urine, basically. The next step is an activated carbon filter in order to remove the micropollutants that can be found. And then the last step is a distiller system which concentrates and hygienize the urine in order to have a final product. Our main product is the Urine fertilizer, so bottle that I have here. I'll come back to it afterwards, which is authorized in Switzerland and other countries. And the other product that we can reuse, but not all clients want to reuse, is the distilled water from the distiller as well. So this system was developed for many years at EAVAG in Switzerland, which is an important research institute for water research. And basically, we're a spin-off of this institute and took this technology to develop it further. The end product, which I showed you, is a liquid fertilizer. So you can see it's brown. It's because it's concentrated, 15 to 20 times concentrated urine. It's now authorized in Switzerland, Austria, France, and it's ongoing for Germany as well. In the European Union, it's a bit complicated because some countries need a supplementary permit. Some others accept directly if you have other countries already accepted. So we have to do step by step, but it's on a good way. Our goal is basically to recycle nutrients, but we realize that on this market, many people don't understand nutrients. So we're trying to translate this also to CO2 avoidance. So I'll come to a few examples of projects that we have now so that you can have a visual idea of what it means, our systems on site. And I will talk also about the challenges of those systems. So basically, this is at the European Space Agency headquarters offices in Paris, France. The European Space Agency is similar to NASA for the Americans out there. And so they are supporting our technology because it's basically, we have a work together on this, and they consider also for it to be a space technology that they want to use in the future. What we observe in this office building is that there's a very good acceptance of the separation toilets. The advantage of those toilets that maybe people don't really need to know that the urine is separated. They don't really realize it. It's a site where there is a lot of visibility, which is great for a branch and our company as well, of course. We have regular tours given either by us or by the agency itself. And people are able to ask questions, see the system, smell the fertilizer, which is an important part, smell the system working as well, which doesn't smell like urine. And the goal, what was planned originally for this system was to treat about 200 liters a day, so about 53 gallons. I hope that my translations of units are going to be right for this presentation. In the end, we rather have less than that. And one reason we expect is because there is much more home office than was originally planned. Because when we planned the system, it was before COVID, and this whole office building was built quite differently than was originally planned. What we observe also from the clients in those systems and buildings is that there is also a big fear of odors and danger and the fear of the danger of ammonia. So this is a thing that we have to work on and show that it's not a problem. Until now, the odors coming from urine were not from our system, but from pumps of other places in the building, which had nothing to do with our installation, which is a good sign for us. So that's just some numbers about this building. The amount of yellow water treated per year is 73 cubic. We have about 10% fertilizer production on the volume, so it's about 7 cubic per year. And then we recycle, we're still ongoing for authorization to recycle the water for flushing of the toilets from those from the concentration of the fertilizer. So we would be able to basically spare 66 cubic water of water by recycling it in the system, which at the size of this building is not huge, but it's still quite important and interesting for the client. I'm going to go on the next project. You can ask me questions to the project later or by email also. That's no problem. The next project is in Switzerland. It's called Blue Factory. It's also an office building, but it's much more dense. So it's offices that are rented. And so it has the amount of offices by square meter is much higher. We have about 500 users of the toilets. We expect them. It's still ongoing for the building of the system. We will probably have about 180 cubic per year of yellow water. And that's about 18 cubic of fertilizer per year. And in that system, it's quite interesting because there will be not only urine treatment, but also Aneco is present on that project in order to treat the brown water. And there will also be a gray water recycling system. So it's really the whole treatment recovery, the whole water recovery and treatment. On that project, the most challenging was mainly the permits on the client side, because there were lots of steps that they didn't know they had to do. Not only on our systems, but on the entire projects. And so there is a lot of delay. And for us, that's a big challenge because we plan with the revenue for a certain year and we realize that this project, for example, has a year and a half or almost 2 years delay. So at our size of company, it's still very challenging. The other challenge that we observe or we expect to observe will be the maintenance of toilets and urinals. We know that it works when it's well maintained in the right way, but we also know that it can pose problems if it's not done properly. There were some problems at the very beginning of the project. Now it has been solved, so it seems good. And again, in this case, we see that the clients are quite fearful of odors and potential overflows or other problems, technical problems. So we're trying to find ways to show them that the risk is very low. Very quickly on how we work in our business model. Basically, the idea is that we install our systems in buildings. The client buys the system, and then we maintain and operate them. So basically, those systems are completely automated. If there is anything that we have to work on or operate manually, we would just receive alarms and be able to intervene online. If necessary, we can also intervene on site, but the goal is only to go twice a year on site for normal maintenance and removal of the fertilizer. So we design it so that the fertilizer is removed twice a year and is stored during this time. The fertilizer should be sold in large quantities, if possible, for the project, because as you saw, we have quite large amounts of fertilizer produced, 18 cubic in this case, 7 cubic in the other case. So depending on the projects, we expect to sell those bottles or larger amounts, for example, IBCs, cubic meter containers or things like that. And the idea is that with the sale of the fertilizer, we should be able to repay the operation and maintenance of our systems, including the parts that we might have to change. But also, we want to do a revenue sharing with the building owners so that they get a return on investment between 10 to 10 years, depending on the projects.
Nadej, we have 1 more minute for your presentation.
I'm done. Thank you. That was it. So that's just, yeah, you can gladly contact me or ask the questions in the chat or wherever.
That's great. Thanks, Nadej. It's wonderful to hear about the profit sharing with the fertilizer and the building owners. I'm sure that makes it much more attractive to future projects.
We're trying to make it attractive. It's still a challenge to show that it works, but we are on it.
Great. Okay, so we have 1 more presentation in this session. David Hasler is a project coordinator with and technical lead in the Circular Flow Technology Project at AVAG in Switzerland, collaborating on the development of on-site urine treatment technology with focus on transitioning the project from academic research to consumer technology. David will be presenting on on-site urine treatment for public toilets, preparing a pilot implementation in the city of Zurich. So go ahead, David.
Great, thank you. Can you hear me?
Yeah, we can hear you and we see your slides.
Perfect. So this is a project running at Earle. We're quite a bit earlier in terms of our journey to implementation, I guess, compared to the other projects shown here. But nevertheless, it's an interesting stage. We're planning the first implementation together with the city of Zurich. So I want to show you some key aspects of this collaboration. But first, some history on our approach to on-site wastewater treatment. There's quite a bit of legacy in terms of on-site wastewater treatment, technology development at Earle. Lots of them focusing also on source separation and urine treatment. And the probably most well-known are blue diversion and blue diversion autarky, which were developed in the course of the Reinvented Toilet Challenge. So we took or started with our project Circular Flow Technology after blue diversion autarky, and the technology we're developing is based on the urine treatment that was developed in the blue diversion autarky. So our first product or product-focused urine treatment is the picture you can see here. And with this step, we're also trying to bridge the gap between applied academic research and find a solution to commercialize this technology for different use cases. So there's a co-development going on between product design and business plan. But before we go to the business case, some very basic information about the treatment technologies here on this slide. It's a 3 or 4 stage approach to urine treatment. There's a first step, stabilization, and also buffering. We have a micropollutant removal, although this is not in the current version implemented. It's still, let's say, lab centered research going on at this step, but we plan to add this module in the near future. Then we have a volume reduction, which is based on low temperature evaporation, together in a closed loop humidification, dehumidification approach, so we can recover water and a dry fertilizer product, which is a urea-based nitrogen and phosphorus fertilizer. This system that we developed during the past 12 months was sort of a hybrid use case approach. We have a modular front end which can be connected to different source separation toilets and urinals, and it allowed us to test lots of different things in the lab and in an internal field test, but it wasn't yet developed for a specific use case. So the step we did from here now was we decided to go to 2 different use cases. One is public toilets with a slightly bigger system, 25 liters compared to 10 liters per day in the current system. And the other one is a smaller system, 3 liters per day for off-grid living, what could be tiny houses or holiday cabins and places like this with a lower demand. Here, for both cases, the urine treatment is paired with different types of treatment for solids, which at that point I do not go into further detail. We have a sort of a bottom-up approach to tackling the public toilet and our different use cases, namely the public toilets. We started in this because it's an attractive niche market that has a high problem solution fit. There's a willingness to pay, which is bigger than compared to other cases. Cities are shifting towards ecological solutions. All in all, this is an attractive place to test the product or the technology. We plan then to scale this up. This is for the something rather for the future, that we can, after first development technology iterations, go to different use cases later on when the number of produced units increase and thereby the cost will come down. So in terms of our pilot case together with the city of Zurich, we couldn't do like a regular product development approach, which is simplified. A simplified version is shown here, which starts with requirement engineering and then goes into a parallel design and planning phase prior to realization. We realized within first exchanges with the city of Zurich that there's sort of a need for first actually finding out what they could use or what they need and where we could meet each other in terms of where our product is at the moment. So there's first a product vision workshop and a conceptual study in this pre-phase, and we figure out together whether these concepts are feasible within the envisioned test. It could also be that we iterate within this project. So this is sort of where we are at the moment. We have a technology that was mainly developed within academia, and to step out of academia with our first implementation partners, we're figuring out together how the solution actually should look like. So there's in terms of this product vision phase, a couple of approaches or scenarios that we discussed together with the city of Zurich, how we can come up with an interesting solution for the urban space here in Zurich. The first scenario was a standalone urinal, which is a mobile solution for public urinals. Scenario 2 would be an add-on for existing public toilets. Scenario 3 would be an integrated version, sort of a back-end solution for existing public toilet infrastructure that's rather like civil engineering heavy infrastructure, which could be outfitted with this back-end technology. And this is also where we settled for the first field test. This is zoom into these three approaches again. So this last one with the existing infrastructure for a public urinal, we found out this is the best case to start. There's a public toilet with 3 urinals, that 1 urinal will be removed and our urine treatment will be integrated in the newly given space. So this is located very centrally in Europe in a public space. It will also allow to add some info panels for communication and make this whole approach to circular sanitation in the public space visible and understandable. In terms of the integration of the backend, we went through different solutions or propositions together with the city of Zurich, that we have a integrated backend in the existing space. We could have a sort of pop-up or add-on backends with additional urinals and leaving the existing infrastructure as it is, or we could integrate it within the existing infrastructure. This is, as I already mentioned, how we're going to do it, minus the third urinal, which they offered to sacrifice for this field test purposes, so that we have sort of a service room, which is very comfortable. This is a small diagram or a simple diagram of how it's going to. Also decided to use a three-way valve to because there's already a sewer connection given. Obviously, this is not the goal for the future that the system depends on it, but for the first test, we will have this bypass or fallback solution with the three-way valve, which will be activated in terms of, or in the case of something that goes wrong with our treatment system. It will also have a connection via G5 probably to let us communicate and gather data, but also change parameters remotely. This is something we are anyway planning to integrate within our systems. That is, there's a remote maintenance or remote monitoring will be possible, and this is the first time we'll actually be able to test this new control system and data monitoring system. So what are the goals? Learning, learning, learning. I guess I do not have to explain this to this audience. It's very important to make this step to the field and check whether it works, because it's not the same as in the lab. Obviously, is it useful? That's a bit of a provocative term, or it's useful to some people, but does it appeal to a wider audience? What are the reactions there? And also, how much does it cost? We need actual realized service and maintenance scheme that allows us to come up with closer values for this operational cost than just estimating them out from where we are now. The backend integration by itself has some challenges, which we are very closely collaborating also with plumbing services from the city of Zurich. And then our product and the process, it's also a test for long-term stability. As I already mentioned, remote monitoring and control is a new aspect that we want to make first experiences. And we also hope that this will be sort of a blueprint for other places and other similar cases where we can scale up this approach. And then obviously also very important, what's the user acceptance? How good can we control the emissions of odor or noise? And already mentioned the factor about the common interest for also people who are not familiar with this approach to circular sanitation. And this is it. This is the team. It's Michael Riechmann, me, and Kai Udert working on this project. And we are also preparing to spin this out of Airwag in the near future. Thanks a lot, and welcome to answer any questions.
Thanks, David. Thanks for your presentation. It's wonderful to see what you all are working on. So let's see it. We have a few minutes for Q&A. Is there anything that came through in the chat?
So we have a question for Earle and then a question from Nancy for everybody.
Okay, so first up, question for Earle.
Okay.
From Christine Johnson. Where or was the urine ultimately used for fertilizer?
Yes.
We've received permission from our town board of health to use Cubies or any container, put them in these 55-gallon drums. They prefer us to have them taken away by the wasted company. But most people want to use the urine on their own property for fertilizer, and they do that. And it's sort of
The Board of Health approved it for us to do
did
that.
they do that? Okay, Board of Health said okay for us here now,
If
but
you
you
do-
have to do it on your own property. That was the technical limit. You can collect on your own property. You can store in these plastic drums on your own property. You can use it on your own soil. You cannot take it off your property.
So when wasted takes it, where does it go?
I believe it goes to a sewer plant somewhere and it's put into the sewer.
I see. So that because of that regulation, that urine is not being used as fertilizer, but if people want to use it on their own land, they're able to do that.
Yes.
And
It goes to MASSTC.
Uh,
We have folks
we-
here on site saying that it goes to MASSTC, and they're going to use it there, or what are they going to do with it?
They do
Bring
have
it.
plans.
We
They
can
do
have
have-
Bryan. Bryan's on the call.
Yeah, let Bryan.
Bryan, what are you going to do with the urine when you get it?
We're gonna play around with it. We can do a lot within our fences without regulatory approvals right now. So yeah, we have about 1,500 gallons in a storage tank from that project, and have been using it for various application testing projects.
Okay. So hopefully the regulations will come through and you guys can use it.
Right.
Yes.
Okay, great. Let's see. Next question from Nancy Love to General or everyone. Does anyone know if we have a standard method for calculating CO2 offset? Is this something we can standardize so we can compare projects easily and on the same basis?
But we have to talk about that the wastewater treatment doesn't even.
Yeah, so it's quite difficult. If I may add something. So we've been trying to do that, but the difficulty that there is that every wastewater treatment plant is very different and has very different data. So that's just within Switzerland, which is a very small country. There is a PhD thesis which did a life cycle assessment on different urine sourced fertilizers and just also untreated urine, which I could try to share the name of in the chat, which is very useful and interesting. So they really did this with this goal. We usually base our numbers on those, but I think it would be very depending on where you are and what the surrounding context is.
Anybody else have any thoughts on that? We've got some in-person questions. Different question.
Someone just Remy posted in the chat.
Okay, well,
Do you want
do you want to address that question, or you have a new question?
Yeah.
The CO2, yeah. When do you want to come up here?
Abby, come on.
Come up to the mic.
Sorry.
So we're still on the CO2 question, and then if you have an additional question, you can come up and ask it.
Is there anywhere I should specifically?
Yes.
Okay, so we have methodologies in LCA where we know the grid is very different depending on where you are. So I imagine there could be a standardization of applying local wastewater treatment, trade. I don't know what they call it in LCA. Sorry? Oh, so I imagine you could kind of treat it the same way. So in this location, we know the grid is this combination of fuels. So the carbon footprint would be this if you plug it in that location. Yeah. Well, sorry.
What did Nancy say?
Oh, Nancy said that we need to have a standardization of practice to quantify CO2 offsets for the industry in order for it to be kind of disseminated, right? Right. Agreed.
Thanks, Andy. Okay, so next question. Steve Jones to Nadej. What were the problems at the start of the Blue Factory?
So the main problem is actually Blue Factory still hasn't started. It was supposed to be installed more than a year ago already, and it's been delayed and delayed. But when you ask about maybe you ask about the problems I mentioned for the urinals and the toilets, maybe is that what you were asking about? I guess that was it. So the urinals, there was there were some smells coming out of the urinals very quickly after the start of their usage. And actually, we realized very quickly after a few phone calls and people going there and trying to understand that the cleaning team hadn't. So first, there was a problem in the cleaning where some urine was coming out of the urinal and basically accumulating under it. So obviously, yeah, that smells. I mean, if you don't clean it properly, that smells. And then the other problem was that the sanitary installer, the plumber, didn't install. So it was supposed to be a dry urinal, and they didn't install the correct odor trap. It was an odor trap, which was supposed to be for a flush urinal. So that was not adapted. And that was the problem of the company delivering the urinals. The toilets, so for the safe toilets, I've been working for a while on here at EAVAG, we have quite a lot, and I'm observing how they're evolving. And the problems we see is that there is some clogging of this odor trap by paper. So that's often a problem more and more now. And we don't really know how come there is so much paper getting in there. One reason might be because of some of the flushes that don't actually work properly. And then, but the odor of the urine, the safe toilet is really not. It's no problem. I hope that answers your question.
Thanks for that, Nadej. So I believe that we are out of time for this session, and we're going to have a quick break.